Good evening again. Up till yesterday, we have covered up to the point of Bernoulli distribution. Earlier, we have explained that we are taking the concept of probability because we are first covering the concept of noise from the communication systems. In order to understand noise, we need to understand the basic of probability. So that is the reason we have taken up the concept of probability in order to understand noise. And till yesterday, we have discussed various definitions of joint probability, conditional probability, intersection, union, independence, mutually exclusiveness, and various notations and expressions for them. Along with that, we have given the definition of random variable. We have also given what is a joint or conditional random variable. We have given the definition and plots of probability density functions and probability distribution functions for both the discrete random variable and also the continuous random variable using the uniform density for continuous random variable. For discrete random variable, the probability density function is analogously called as probability mass function, which is formed by series of impulses. And the probability distribution function for the discrete nature random variable is a staircase one. When it comes to the continuous case, the density function is a continuous one, and the distribution function is also a continuous one if the density is a continuous one. And the nature of the discrete probability distribution function in the continuous case is that it is always increasing, just like its discrete counterpart. So we have seen again, as a conclusion, we have also seen about the Bernoulis experiment. In this session, what all we are going to cover, let me mention first. We will again go back to Bernoulis experiment once. The second one we are going to cover is binomial distribution. The third one we are going to cover is about the other Gaussian distribution. We will just introduce what is Gaussian distribution in this session. In later sessions, we will see what are the various concepts related to Gaussian distribution. After that, we will going to see what is the moments whenever the probability density function is given, how to calculate moments, we will see that, and what is the central moments. Now let's start with the Bernoullis experiment. Bernoullis experiment is that kind of experiment which is only having two outcomes. The outcomes, if one of the outcomes probability, let's say outcomes are A and B, and here in the case of Bernoullis experiment, if probability of happening of A is P, then it should follow that probability of happening of B is 1 minus B, 1 minus P, because the probability of the experiment is 1. This concept various times I have already explained, but still I am explaining because in order to remove any stray confusions, probability experiment is always 1 because the probability of happening of the experiment is always 1, and the experiment, the result can be event A or event B. There is no other event. In such a case, these two events are complete events. They are completing the sample space. The sample space itself is having two events. The sample space itself is having only two events, A and B. And here in this case, there is something else also. A intersection B is equal to 0. That is, these events are I have given this term various times till now, mutually exclusive. So whenever the events are mutually exclusive, then their probability of intersection or probability of both the events happening together or probability of A and B is simply 0. So in such a case, the probability of A is 1, then the probability of B is 1 minus B, because the only possibilities are A and B. And we also know that probability of A or B is equal to probability of A plus probability of B minus probability of A intersection B. Again, this part is 0. The reason is that they are mutually exclusive. So probability of A union B is equal to probability of A plus probability of B. Here, sample space yes, the experiment is having only two outcomes, A and B. There is no third outcome. In such a case, the probability of A union B is simply the probability of A or B. Of course, A or B are only there the events of the sample space. That is simply probability of A plus probability of B, that is simply 1. The reason is that there is no third event in this. So now if you assume the probability of A is P, then probability of B will be 1 minus P from this equation. So such a experiment is called as Bernoulli's experiment. And tossing a coin is also one of the Bernoulli's experiment. Here in this case the probability of P is simply half. Probability of P is half. So this is about the Bernoulli's experiment. Now let us see what is a binomial distribution and binomial experiment. Well, the binomial experiment is like combination of or repetition of various Bernoulli's experiments. So here what I wanted to say is, suppose if you take a Bernoulli's experiment, say for example you take a tossing of a coin. So if it is a fair coin, earlier we have also discussed, the probability of head and tail are simply half and half. Now let us assume that it is not a fair coin. So in that case, probability of head and tail are not half and half. Let us say they are P and 1 minus P. From the nature of the Bernoulli's experiment, we have taken it as 1 minus P because it is P. Now in this case what is happening is, say for example that experiment is repeated n times. So if it is repeated n times, then out of n, say y times head has occurred, and of course then n minus y times tail has occurred. In such a case what happens is, the probability associated with this kind of outcome, y times head and n minus y times tail, is probability of y times head. Here let us put a small condition, this y times are continually happening for the first y times. So the first y times the experiment is performed up to y times head has occurred, and after that n minus y times tail has occurred. So the outcomes are not overlapping. The first y times are simply head, after that there are simply tail. In such a case the probability is, if the probability of occurrence of head is P, then P power y into 1 minus P power n minus y. Probability of y times occurring sequentially first. So hope with a sequence in the first part of the trials, and after y times then there are n minus y tails. So the total probability of such an outcome is P power y into 1 minus P whole power n minus y. to this. So now, if suppose the question is, there is no condition like the first time, there is no condition like they should occur in sequence. If sequence is not followed, if sequence is not followed by the outcomes, in such a case, the y can be anywhere in along the trials. Say for example, if the heads can be randomly dispersed among the sequence. Say for example, the first is head, after that some tails are coming later head, but overall the number of heads is same. And number of tail is same. So in such a situation, the probability of such an occurrence is, let us call the event, let us give a name of the event as L. Such a probability of such a event is given by binomial theorem and binomial expression. So now let's go to the next slide. In order, so we are considering the experiment where heads are coming out as outputs for y times and tails are coming as the outcomes for n minus y times, and in such a case, but the order of heads and tails is random. So this way, where I have given you the sample order, there is no particular order of occurrence of head and tail, but we only know the total number of times for which head has occurred for y times, and total number of times for tail has occurred is n minus y times. In such a case, if we want to find the probability of heads occurring y times, we have to apply, or we have to use the binomial theorem. So using binomial theorem, such a probability of such an event L is actually given by n c y p power y 1 minus p power n minus y, where n is the total number of events, total number of times that coin is tossed, y is the number of times heads has occurred, sometimes we can also say y as number of times favorable outcome has occurred. Here we have considered the outcome as head and we want to calculate the probability of outcome of y times head. So we have taken the favorable outcome as occurrence of head, and of p is the probability of occurrence of head in a single trial. So probability of occurrence of favorable outcome in a single trial. Here, since it is a Bernoulli experiment, the other probability occurrence of tail is given by 1 minus p, but 1 minus, if it is, if the so if they have given that the probability of the other event as q, then you may take q in place of 1 minus p if q is given. Since it is a Bernoulli trial with only two outcomes, a binomial theorem is also applied for only two outcomes, but since it's a Bernoulli trial, it q is simply given by 1 minus p. So now let's go further. I will give another example for application of binomial expression. So consider an expression where a coin is tossed 20 times. So n is 20 times, and assume it is a fair coin. So p is simply half, 1 minus p is also simply half. Now let us plot the probability of occurrence of heads small n number of times, or let's take y itself, small y number of times. Now if I plot this probability on the scale, so let me take the y-axis as probability, let me take the x-axis as probability. So let me take this as 0, this as 1, this as 2, and so on, 10, 11, 12, and so on, 20. So here the probability, here it is y is the number of times head has occurred out of n times. N is simply 20 because we are tossing the coin 20 times. The probability of occurrence of 0 heads out of 20 times is there because all could be tails. It is some value is there, that is actually given by, this one is actually given by nc0 p power 0 1 minus p power 20. You can calculate this one, 20c0 half power 0 and half power 20. It will be giving you some value, some limited value, very less value. But as you go toward the right side, up to the value of 10, the probability of occurrence of 10 times heads, the probability is simply increasing. Just like this. So again, since it is a discrete function, we may represent this using discrete impulses. But again, if you further increase, if for the 11 number of times, 12 number of times, the probability is again decreasing, and 20 will be same as 0. From the expression also we can understand, and intuitively also we can understand. But the probability of occurrence of 10 is like 0.1789, nearly equal to 0.18. This is also can be obtained like 20 c 10 p is half power 10, because here 10 times the favorable outcome as head has occurred, p can be taken half here, and 1 minus p is also half. Here 20 minus 10, here should come 20 minus 10 is simply 10. So if you evaluate this one, it will be approximately equal to 0.1789. So this way the variation of probability with respect to number of heads that is occurring out of a tossing of a fair coin is plotted in this plot. This is the probability mass function that we have discussed yesterday. If we are doing a summation of the same, then we will be getting what is called as probability distribution function. So let me give the approximate plot of that probability distribution function here. Up to here it is 0, here impulse has occurred, so it will take the magnitude of the impulse. Again it this way, the staircase way, it is increasing up to 10. Again after that also it is increasing, but the magnitude of increase will be reducing, and finally at 20 it will be, after 20 it will be, here 20 also will be having a little increase because impulse is there. After that it will be constant at 1. Kindly adjust because I am not having proper space here. So the final value of the probability distribution function will be taking it as 1. So this is a probability distribution function of tossing of a coin 20 times. Okay, now let's go further. I am going to introduce you to Gaussian distribution using the expression. Let's go to the next page here.